Hi everyone, it's Josh here, and today I'm going to teach you about integration by parts. First off, I'm going to show you where the formula comes from because it's not very intuitive when you see it. So it's actually the inverse of the product rule when we take a derivative. So we all know, hopefully we all know, if not, I'm going to show you, that if we have two functions, we're taking the derivative of two functions multiplied by each other, f of x, g of x. That's going to equal f prime of x, the derivative of the first, times the second function, plus the first function times the second function. Now, if we integrate both sides, and I'm going to try to do this in a different color, and we solve for this one right here, we're going to get, first off, the derivative, the integral of a derivative is just the function f of x, g of x. We're going to get f of x times g of x minus the integral of f prime of x, g of x, and that's going to equal the integral of f of x, g prime of x. So it might not look very useful when we see it at first, but our goal basically of integration by parts is if we see a function like this, we're trying to take the antiderivative of two different functions basically multiplied by each other. We're going to try to make it into a derivative, or try to get an integral right here that we can easily integrate. So we can't really easily integrate this integral right here when we see it, but we can easily, hopefully, integrate this integral, whether it be by a simple standard integral, or whether we use another method like U substitution or trig substitution. So that's our goal, is when we see this function, if we take the derivative of one of the functions and the antiderivative of this part of the function, the g of x, g prime of x right here, because we're taking the antiderivative of that we're going to get this integral circled right here that we can easily integrate. And so that's why integration by parts is really useful. And you're actually going to see it where it actually equals right here. This is going to be the integral. Oh, I need to change to another color. It's actually going to be that f of x is going to be u and g prime of x is going to be dv, since that's a derivative. And that's going to equal the uv, because from dv to v, because we're actually going to take the antiderivative of dv minus the integral of v du. That's the standard formula that you're going to see. So I'm going to go over some examples with you. So the first example is going to be the integral. Got to get a different color here. The integral of x cosine of 5x. So our goal here is that we're going to get another integral where if we multiply the derivative of one of these and the antiderivative of another one of these, we can integrate it really easily. And a really good way to remember which one is, to take the derivative of or make your u so that we get that simple integral is Liot, which is, type it out right here, which is logarithmic, inverse trig, algebraic, trig, and exponential. So right here we have a trig and an algebraic function. So we're going to make the algebraic function the u to get a simple integral. So we're going to have the u is going to equal x, du is going to equal 1. Our dv is going to be cosine of 5x. And to take the antiderivative of cosine of 5x, we're going to use u substitution. So I'm actually going to go back to this page in a second, but I need to explain u substitution to you first. So if we're integrating, taking the integral of cosine of 5x, u substitution is essentially the inverse of the chain rule. We're undoing the chain rule with u substitution. So we're going to make our u, because that's the inside function, our u is going to be 5x, and then du is going to equal 5 dx, and then 1/5 du is going to equal dx. We bring constants over to the du side, and we keep like x's and stuff on the dx side. So then we put in that u here, cosine of u, and we're going to have a 1/5. I'm running out of space. A 1/5 before the cosine of u, because that's our constant we got there. And then the antiderivative of cosine is sine, so it's going to be sine of u, 1/5 sine of u. And we're going to then put our u right here. We're going to put our u in there. So that's going to equal 1/5 sine of 5x. And if we actually take the derivative of that and use the chain rule, if we have f of x, f of g of x, we know with the chain rule that it's going to be f prime of g of x times g prime of x. So if we take the derivative of that, it's going to be, the derivative of sine is cosine of 5x times the derivative of our g of x right here is going to be 1/5 times 5, and then we're going to get back to our original cosine of 5x. So now we're going to go back to that problem since I've explained u sub to you. So we have the u, the du, and so we got our v as v equals 1/5 sine of 5x. Running out of space here. All right, so our 1/5 sine of 5x. So I always write down the formula uv minus the integral of v du to let everyone know I'm doing integration by parts, and also because it's really helpful for me to keep myself organized. And so we have our u and our v, so we're going to do u is x times 1/5. I want this thing right. 1/5 sine of 5x minus the integral of v, which is 1/5 sine of 5x times our du, which is just 1. Well, look, we can easily take that antiderivative, which is the beauty of integration by parts, whereas we couldn't easily take the x cosine of 5x. So again, we're going to do u substitution here to solve this antiderivative, and u is going to equal 5x. So that means that 1/5 du equals dx. And so we're going to have 1/5 sine of 5x minus, well, the antiderivative of sine is just negative cosine. So we're going to have the integral of 1/5 times 1/5 there, which is going to be 1/25 times negative cosine of 5x plus c, which is our constant of integration. And so I have to add a page here. If we have, just simplifying this down, you distribute the negative, the final answer is going to be 1/5 x sine of 5x plus 1/25 cosine of 5x plus c. So yeah, that was, that made our problem really simple. That's the point of integration by parts. We want to get an integral, from two functions multiplied by each other. We want to use integration by parts to get an integral that we can actually integrate. So then, of course, we can use integration by parts twice, actually, which is the next example that I'm going to show you, because that can be really tricky. So if we have this function right here, the integral of that, we know we're going to have to do integration by parts because they're two functions multiplied by each other and we can't do u sub at all. So that's a good lead, a good nudge that, we're going to do integration by parts, a good hint. And we're going to do it twice because if we take the derivative, this is going to be our u because it's algebraic. If we take the derivative of this, we're going to get 2x times, the antiderivative of cosine of x, which is sine x. We can't do that really easily, but if we integrate it again and the double, double derivative, the second derivative of x squared plus 2x is just 2 times the antiderivative of cosine, or, plus a trig function, which is really, we can integrate that really easily. So we're going to make our u equal to x squared plus 2x. And so our du is going to be 2x plus 2. And our dv is going to be cosine of x. So our v is going to be sine of x. And I am actually running out of time here on this screenshot thingy. So I'm going to have to do this quickly. So we're going to have uv minus dvu. uv minus integral of v du. And uv, I'm going to have sine of x, right in here, sine of x times x squared plus 2x minus the integral of sine of x times 2x plus 2 dx, which I don't have enough space to write the dx. So if we do integration by parts a second time, for this one right here, our u is going to be 2x plus 2. Our du, running out of space here, is going to be 2. Our dv is going to be sine of x. And our v is going to be cosine of x. So I don't have enough space, so I'm going to have to write a new page here, do a new page. So then if we have what we originally had, sine x times x squared plus 2x minus, and then this is where we do our integration by parts because we had that integral, I actually forgot what it was. It was sine of x times 2x plus 2. And I'm totally running out of time here. But anyway, we're going to get 2x plus 2, if we do the uv minus dvu again, times cosine of x minus the integral of 2 negative cosine of x. And it's always important when we do another integration by parts that we want to parenthesis this, because this is going to be minus, and we're going to have to distribute some negatives here. So the final answer, when we actually take the integral, that's a simple integral right here that we can actually do, which is awesome. And so the final answer is going to be sine of x, x squared plus 2x, minus 2x plus 2 cosine of x, minus 2 sine of x plus c.